Recording in progress.
Okay, so welcome back, folks. Today we're going to be focused on completing our lab exercise 4. So I'm going to do a little bit of review. We're going to actually as well um, be able to look at the solution of lab exercise 3 to make sure you guys have a solid understanding of that. I will not be accepting submissions of lab exercise 3 anymore, but I have now uploaded a solved lab exercise 3. So if you check the repository that's linked in under T163. I've also posted a separate link, but you check the repository, you switch branches, you can find the solution to lab exercise 3 on its own branch. So just the tip of that branch is going to be the solution. Okay. If you ever want to submit your work and make sure that I have access to a specific submission, which you should do. This is a requirement actually for the lab exercises. You don't give me just the repo link. Okay, so see the URL? This is what you would give me if you just wanted to give me the whole repository. But actually, I'm not asking for the whole repository. I'm asking for a specific part of the repository. That is the part you're trying to submit. So um, in the physics lab overview, you know, it's gonna say, do this stuff, blah 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 blah, and then what you're supposed to do when you submit is uh, link to the commit representing that submission. Okay, so that's not the same thing as a link to the whole repository. If you give me this, then I won't actually be able to grade your work properly, because I would have to go digging around every individual commit, and then there's doubts as to whether or not you completed it on time because there's lots of other commits after what you submitted, and you may receive a grade that you don't want, or you may receive a late penalty because there's work here after the deadline of your submission. Okay, so to avoid those sorts of issues, I need you to not give me a link to the whole repository when you submit. Okay, I need you to give me a link to a specific commit. So and actually there's another option that I'm okay with as well. So don't give me this, but do give me, if you want to give me a specific commit, you can go to find that commit by clicking here, this number of commits or whatever, and then find the commit that you want to submit. Let's say this is, I completed lab exercise 3, it's done. Now I want to submit. Give me this link. So there's a little button here that's going to let you browse the repository at that specific point in history. So it'll show, this is what the code looked like this is what the whole project looked like at this specific point in time. That's the URL I want you to give me. Okay. Now, a lot of you did it correctly, but some people made the mistake of not doing that, and it can cause problems. Okay. So give me that link from these little angle brackets. You can also copy that link address, right? So, for example, I'm going to paste it in the chat here. That's what you would get, right? And you can see there's a bunch of numbers and letters at the end. These numbers and letters at the end are what we call the commit hash. It's a unique identifier for this specific uh, version of the game, or this specific version of your project. You know, this point in history in your repository. Uh, if you submitted the link for the whole repo, it depend whether or not it's a problem. Kind of depends on what happens when I grade it. So if I can easily find what I need, then it's fine. But if there's any problems finding what I need, then that's on you because you didn't submit it correctly. Okay. For your lab exercise, 1, 2, and 3, those are done. I'm not accepting, updates to those, but definitely for your lab exercise 4, try and keep that in mind, okay? Um, the other thing that I will accept if you do is if you give me a link to a branch. So you can do that too. So if I, on GitHub here, if I go click into a branch, then since I made a branch specifically for lab exercise 3, right? Um, then if I give a link to this branch, you'll see the URL here is actually a link to a branch. As long as I don't touch that branch again, then that's going to be pretty much equivalent. If I do touch that branch again and I submit an update, I commit to it and push to it, again, after the deadline of the submission, when, past the deadline, then there's a problem, right? Then you've done work after the assignment was due, and then it's late, right? But if I just leave this alone, then just giving the branch link is fine. Then what I would do is I just start a new branch for exercise 4, right? So you could branch off the existing branch. If your commits are easy enough to find, they're clearly labeled, then it's probably okay. But I can't guarantee it's okay because lots of people make mistakes. Lots of people, name a commit. Oh, this is lab exercise 3. But then when I actually look at it, they made a mistake in how they labeled it, and then it's like, oh no, actually that was not finished. There's a real lab exercise 3 for real, final version a few commits after or some silly thing like that, right? Um, so I just can't guarantee it, but it'll probably be fine. Um, when I know your work specifically, so you're probably fine, you know. Uh, as you can see by your grading from your uh, first couple exercises. Okay, so here, hang on a sec. So here we're on the lab exercise 3 solution branch. Let me just switch back over to the branch that has some work that was not committed and pushed yet. Um, and I'll jump to that. All right. Anyway, folks, yeah, if you need help like having a good starting point, feel free to just take the lab exercise 3 solution. So feel free to use that to to work on. Okay. So you can totally use the solution to lab exercise 3 to complete lab exercise 4. Okay. What you can't do is submit it for your lab exercise 3. I'm not taking that. Okay. So lab exercise 4, what we're asked to do is half space collision shapes. Let's review that a little bit. Where's my little diagram? Where's the little diagram? Oh, there it is. Yeah. All right. Well, let's review our task again. So we recall that what we've done is we've created some kind of class representing our different shapes. So we have a half space. Maybe it's not as well designed as it could be, but we're just trying to get something working. Um, we did end up with this idea of a shape enum and an object class, and our specific shapes inherit from our object class. Like I did say before, I do recommend that you split up the shape from the kinematics. Um, if you were actually making a physics engine. But you know what? For our purposes, it's fine if we just keep it kind of simple and just assume that every physics object has a shape. Uh, and vice versa. Every shape also is a physics object. Um, although it did cause us to have to add this little extra parameter is static that would basically tell our physics engine to not use these parameters, the velocity and mass and stuff like that, because we had to have in our physics simulation some objects that do not use gravity and do not use velocity. So, as an example, we have this ground plane that we're supposed to be able to just, move around and rotate, but it has nothing to do with like the actual kinematics. So it's not going to move itself. Um, all right, but what we're missing is we need to make sure that these two are green when they're not touching, and then when this ball crosses this line, that's when they should both turn red. Right now, it's not quite doing that. But in theory, we should be able to adjust this, right? So there's a couple things wrong with this. One is that this distance calculation is not reasonable. We're measuring the distance between these 2 points, but as you might be able to tell, that is not really the relevant information, actually, right? Because I can move this arbitrary point that is on this half space around, and it changes the distance, but really that point there doesn't mean anything in terms of our half space. It's just part of how we've defined it, and it's part of what we're using to be able to allow a game designer to control it, to move this position around. But the point here is just an arbitrary point that we've decided. We've defined our half space as a normal vector, or an angle, actually. We've defined it as an angle and an arbitrary point on that space, just because that would be convenient for a game designer to use to create a game situation, a great game scenario. That's it. We did it. We defined it this way because it's convenient for designer. Which actually a lot of things that you'll have to do in game development are going to be like that. You're going to design it so that it's convenient for the game developers. Um, okay, so we have at least defined our half space. What we haven't done is this stuff here, the collision detection. So what we need to be able to do is we need to be able to think about how do we accurately figure out the distance between this circle, any circle, and any of these half spaces. Okay, so the distance of this circle from this half space, remember that this half space extends infinitely in every direction. It's not as simple as just subtracting the two positions and taking the length of that vector. It's not the same as what we did with circle-circle collision detection, where we really could just subtract the two positions of the centers and then get the magnitude of that difference. So now what we have is that position that we have for our half space is kind of arbitrary. It doesn't really matter, right? But it sort of doesn't matter. But we can still use it, actually. Um, so really, the distance between this circle here and this half space, okay, it's going to be related to the distance between this circle and this arbitrary point. But if this arbitrary point can move anywhere along this plane, how could that be? Well, the reason is the issue is what we need is not just this straight line distance here. What we need is the distance perpendicular to that plane. This is what we need. Oops. That's what we actually need. Okay? So what we have right now is this, right? So the distance between the center of a circle and some arbitrary point. But what we want is this, the distance between the center of the circle and the line representing this half space. Okay, and we need this to be a 90-degree angle, right? We need it to be perpendicular. And we need this to be the case no matter which way this thing is rotated, right? If it's rotated this way, what we need pretend that lines up properly, right? Is we need this to be 90 degrees, right? And we need to be able to measure this. The projection of this arbitrary line here, the projection of this onto this normal vector. So it is actually this displacement that we're using. You know, we're just taking this arbitrary point, okay, and this center of the circle, and we are using that vector. But what we're doing is we're taking that vector and we're projecting it so that we've eliminated all of the component of this vector that is parallel to the plane, because we've determined that that's not relevant to us. The part that is relevant to us is the length of this in specifically the direction that is the same as this normal vector. That's what we need, right? When we looked at it in the simplified case, you know, just vertical, right? When you have this, this horizontal line, then you notice that the vertical position is the only thing that matters. The horizontal position doesn't matter. What really it means is it's the position along this normal is what matters. So how do we do this? How do we get this projection? Let's see what we have. Where do we have it? Right now we have our function circle half space overlap. What it's doing is it's trying to it is getting the displacement from the half space to the circle. That's what I've done here. Actually, last week I think we did it the other way around, but I decided I wanted to make it point in the same direction as the normal. Um, So I've taken the circle's position, I've subtracted the half space, so that it would be, I would get a vector that points like that, right? So I'm getting this vector, all right? Something like that, or in this case it's that vector, right? So from that arbitrary point on the half space towards the center of this circle. So I have this vector right now, right? But I need to get this vector. I actually don't need this to even be a vector as much. I kind of just, you almost just need its magnitude, but yeah, we'll see that. Hang on. Okay. So if we remember anything about vector projection, then how could I get this vector and then turn it into a vector that just points along the this direction? So I have this vector and I have this normal. What do I need to do? I have this vector and I have this normal. Ideally, this normal vector is of length 1. Okay? That is important to us. So, how much do you guys remember about vector projection? How much do we remember how that works, or what it is? Not too much? Let's do let me describe vector projection again for us. All right. So I want you to think of vector projection as though you have a sun a shining sun. Okay? And it's casting light rays, and your projection is the shadow of something. Okay? So let's say I take this arrow over here. Okay? I have this arrow here. This is a vector. V. Hang on. Let me make this. Let me scale this differently. Okay, and then let me make this the x-axis. All right, so I have a sun, and the sun is shooting light rays in a certain direction. Okay, so you can kind of imagine a vector projection operation like you're taking the shadow of something. Um, so if I want to project this vector v, projection of v onto x-axis, right? If I want to project v onto the x-axis, what I'm going to do is I will be figuring out what is the shadow going to look like along this x-axis. It's almost like you're imagining that you're shining a light. Okay? And what you're doing is you're eliminating every piece of this vector v that is not aligned with that x-axis, that other vector that you're projecting onto. Okay? So what do you get? You get a shadow here, like it's on the ground. And the shadow of that is what you're getting. Okay? And it will produce a vector. Okay? This is that vector projection that you're going to get. Okay? So if you have this vector v and you project it onto the x-axis, you're going to get v projection of v onto x. Sometimes you'll see it you describe with a subscript and whatever, but just fancy ways of writing this. You're going to get this other vector here. Okay? That is your vector projection. Okay? The length of that vector projection, that is this thing, but if you're just figuring out, if you just take the length of that, that would be called the scalar projection. If you just care about the length of it. Although, if you do dot product, sometimes what you'll hear dot product called is scalar projection. It will tell you something like this. So instead of getting a vector, you're going to get a single number in scalar projection. Okay, let's do an example. So let's say v is equal to 4, 8. Okay, and then let's say x-axis is equal to, well, 1, 0. Can we calculate this? Can anyone pull up their math notes and find the formula for vector projection? There's a dot product in there somewhere. So it's going to be A dot B projection of, so A onto B the formula for this is going to be A dot B, okay, over, you could say it's A dot B over B dot B. Uh, there's a few different ways you could describe it. Um, times B. That's one way you could say it. Another way you could say it is A dot B times B divided by the magnitude of B. Okay? So these are actually equivalent. It's just rearrangements of the algebra. So let's see what when is posted. Yes. Okay, cool. So let's break this down. This bit here, the B divided by the magnitude of B, essentially that's just normalizing a vector. Do you remember what normalizing means? All right. Make the magnitude 1. So this part of this equation is basically just saying, okay, we don't care about the actual magnitude of this vector we're projecting onto. We just want the direction. That's all this is. This part here is just trying to get rid of the direction part. In fact, if this vector is already of length 1, you don't need to do this. You don't need to do, if this is 1, 0, the vector is 1, 0, that has a length of 1. You don't need to be doing 1, 0 divided by the length of 1, 0, which is 1. So 1, 0 divided by 1. You don't need to do that, right? So if our vector is already normalized, you don't even need to do this part. If you're guaranteed that it's normalized, you don't need to do that part, right? All that is just trying to get it normalized. And this is dot product. Dot product, also called scalar projection. It tells you the length of the shadow of A on B and also the sign tells you if A and B are in similar or opposite directions. I.e., if, hang on, if the dot, if A dot B is negative, that means that the angle between them is greater than 90 degrees. If the dot product is positive, the angle between is less than 90 degrees. And if it's 0, the angle between them is equal to 90 degrees. Okay? So if this is A, and then you have a circle, sure. If you take the dot product between these two, that are the same. Wait, hang on. Okay, you're going to get something positive, like 1. If they're the same length, if they're if they're length of 1, let's say, um, if then you're going to get 1. If they are 90 degrees from each other, then you're going to get 0. If they are 180 degrees from each other, then you're going to get -1. Okay? And the other side also works. If they're 90 degrees from each other in the other direction, it'll also be 0. Okay? So dot product is interesting that way. It does that. Okay. Um, do we remember how to calculate dot product? Do we remember the formula for dot product? Can we try using that here on these example numbers? What do you get? So what you're gonna so what you're gonna do is you take the x components, you're gonna multiply them together. V dot x times x dot x, okay, uh, plus v dot y times x dot y, whatever. And then what you're gonna get is just 4. So if you look at it, the y component here is 0, right? So what that's going to do is it's going to make the y component of this v vector does not matter. The x component is 1. So it's going to make this x component of this v vector matter entirely. Okay? So in essence, this vector here of 1, 0 is kind of deleting everything that is in the y-axis and only taking what's in the x-axis. Okay? So you're going to get a value 4. What does that mean? 4, and that is positive 4 specifically, that's positive 4. The value of positive 4 means that, first of all, the vector v and the x-axis vector that we're using here are in the same direction. So they're less than 90 degrees apart from each other. Less than 90 degrees difference between them. Second, it's telling us that the length of this shadow of v onto x is 4. And so if you were to take that, this a dot b thing, right, this is v dot x, and then you multiply that by the normalization of the second vector, right? So if you did, let's say, x divided by the magnitude of x, it's just 4 times 1, 0. Right? So the vector projection that you're going to get is what? 4, 0. Yeah. So the difference between the scalar and the vector projection is really small. It's really slight. This is the scalar projection. This is vector projection. It's just the one step further where you multiply it by the direction. Okay. Um, in this case, this vector was normalized already. But if it wasn't normalized, this bit right here would handle that for us. It would make it like length 1. Taking this vector and dividing it by its own length would give us that. I'm using these vertical bars to note the getting the length of that vector. Okay, so that's really what vector projection is. Now, I'll be honest, we don't actually even need the vector projection part to solve our problem. This could be relevant in the future, but we actually don't even need this vector projection part right now to solve our problem, because what we want to determine um, is just this distance, okay? And the scalar projection tells us the length of this vector. We don't really need to also multiply it by the normal vector here to, to get a vector in the end. We don't even need that. We just need the dot product. That's all we need. And the dot product will also tell us it'll be positive or negative. What would it mean if we did this, right? We take this vector, if we took this displacement vector from the half space to the circle, and we took the scalar projection of it, if we took the dot product of this and the normal, it will give us a number that is just one number, positive or negative. If it is positive, what does that mean? That means this and this, there's less than 90 degrees between them. What would it mean if it was 0? If we took this vector and you took the dot product of it with the normal vector here, and then the answer was 0, what would that mean? 90 degrees. What does that mean in relation to the circle? Let's construct an example where it's 90 degrees. An example where it's 90 degrees would be, let's say, like this, right? Which would mean the circle is directly on the line. Cool, interesting. Okay, so if the dot product is 0, we're on the line. If the dot product is positive, we're above the line. Can you guess what it means now if the dot product is negative? So if that dot product is negative, what's it going to mean? Then we're actually behind the line. Even just by a little bit, it would count, right? Because if this vector, as this, see, here's positive, here's 0, here's negative. Positive, 0, negative. And it works the other way around too. It works on this side. Positive, 0, negative. Positive, 0, negative. Same stuff, right? Right? So this d here, this distance here, this is really the dot product. This only detects if the circle center is, the side of the circle is on the line. Yeah, but what if you have a big circle? What if you have a radius? The great part is the dot product, it also has a magnitude. It doesn't just have a sign. So when it's positive, we know we're on this side. But the amount it's positive tells us the distance as well. Let's look back at this example here, this projection thing, okay? So what we got when we took the dot product here was positive 4, okay? that was the length of this shadow on this x-axis. And if we take this in any and do any other kind of projection in other directions, it doesn't need to be specifically the x-axis, right? So if we took any other vector, okay, and we take these two, right? If we take the vector projection, it's gonna calculate this basically this parallel component, right? So you can imagine no matter what we do, this vector projection is kind of going to give us this right here, as though there's a 90-degree angle right here, because what it's going to do is it's going to eliminate every part of this vector here that is not in line with B, okay? And it's going to tell us this. It's going to give us this little bit. And this little bit is going to be longer or shorter. The magnitude is going to be greater or lesser depending on what we have right here. So if this is more in line with it, it's still positive, but it's going to be bigger. If it goes the other way, and there's actually greater than 90 degrees between them, okay, what we're going to get is a number that is negative, but small. So that's going to be actually a negative. So that's what's really neat is that just no matter what, it's going to tell us two pieces of information. Not only the angle, but also by how much. And since our normal vector, hopefully, should already be normalized, we don't even need to do this vector projection part to account for that. Now, if it's not normalized, things change, right? So if I, for example, if I did this, if this was a vector of length 8, and then I took the dot product of this, it would not be giving me that same piece of information just doing the dot product alone. So if this was 4 and 8, then the dot product would end up multiplying 4 times 8. Okay? So it would depend on the length of both vectors. It only works this way that we get to skip the vector projection part if we know that this vector is of length 1. Because when this vector is of length 1, then the dot product here only depends on the length of the one we're projecting, right? So that's where if this were not length 1, then it would matter the length of this. But since it's length 1, now when we take this and project it onto the normal, we're getting an answer that only depends on the length of this and the direction of the normal, which is exactly what we want. Okay, so this dot product is going to be more or less positive. In the case of here, right, let's say this is y equals 2. Okay, this circle is at position 4, 5. We don't care about the x position if this is a completely horizontal plane. But its radius is 5. So, you know, the question is, hey, is this thing touching? Here's what we do. That position, we get a difference vector. What's our difference vector between these positions? This arbitrary point, it might have an x component. Let's say this point is it will have 2 as its y coordinate. But let's say it's 1, 2. Okay? So the displacement is going to be, if we're doing from the circle to the plane, we're going to do 4, 5 minus 1, 2. And what are we going to get? What's our answer? Can we do this? 3, 3. Perfect. Very nice. Then, that's our first step. Our second step is we're going to do the dot product. Okay? So we're going to take that 3, 3 and dot it with the normal vector. In this case, what is our normal vector? What is our normal vector? 0, 1. Great. So what would our answer be here if we took these and dot producted them together? 3 times 0 equals 0. Plus 3 times 1. So our answer would be positive 3. What that means is the circle is 3 units away from the half space, okay, in the direction of the normal. Okay, so now what can we do? We have a circle radius, and we have this knowledge that we are 3 units away in the direction of this normal. So, in other words, the displacement projected onto the normal is a 3. Positive 3. So, since the distance is 3 and the radius is 5. Okay, so the distance is less than the radius, so we're overlapping. Perfect. Now, how can we handle it in another case? What about this other case? Hang on a second. Let's do this other circle here, where instead of position 4, 5, it's 4, negative 5. Okay, and let's say radius, yeah, let's say radius 2. Okay, let's do this. And let's keep our point at 1, 2. And this works with the rotated stuff as well. We just happen to be dealing with perfectly horizontal surfaces. But if you do this right, it doesn't matter how this is rotated, because when you do that dot product, it will give you in the direction of the normal, no matter what direction the normal is facing. If it's horizontal, vertical, whatever, it's going to be correct, right? We did it here where it was actually 1, 0, and we did it here when it was 0, 1. It also worked with any direction in between. Okay? All right, so let's try this. We take the projection by we'll find the displacement. Okay, so we'll do 4, -5, minus 1, 2. What's our answer? Three, -7. Okay. So if we do the scalar projection of this onto normal, let's do 3, 7, dot, what's our normal vector? In this case, our normal vector is still 0, 1. Okay, so what do we get? 3 times 0 plus -7 times 1 equals -7. Okay, the length of the projection of the displacement onto normal is 7. So then are they colliding? 7 is greater than the radius of 2, right? So they're not colliding? Wait. Wait a minute. We defined our half space in this way. If something is behind this surface, it should be considered to be colliding. So we need to find some way to, handle this case as well. If we just look at these numbers, we'll say, oh, okay, 7 is greater than 2, so they're not colliding. Ah, we need to deal with the sign. Yeah, we need to pay attention to the sign. So this is true, what it says. The length of the projection on the displacement is going to be 7. But the sign also tells us something. It tells us we're on the opposite side. It tells us we're behind. Okay? It tells us, right? It tells us that this vector here and the normal, there's an angle greater than 90 degrees between them. So it's actually pointed behind the normal. So what do we really need to do here? We don't just need to do is what number is greater. Let's make this more specific. The scalar projection of the displacement onto the normal is -7. So we will do if this -7 is less than 2, then we are overlapping. Is -7 less than 2? It's more than just if negative. You can do it even easier than what you've just written when. That is, what you've written will work. If negative, then it's colliding. Otherwise, if distance is less than radius, then colliding. But you can also just do if the number that you get is less than the radius. So you can try it yourself. Simplify what you've just done, right? Like, let's say, if your projection is less than radius, then overlapping. Right? So think about it this way. If this is positive, right? 5, 4, 3, 2, right? All these numbers, then you're not overlapping, right? 5, 4, 3, 2, all of those numbers, you're not overlapping. Um, At 2, you're just like barely, uh, barely there, right? Um, but you're not overlapping. At 1, you're overlapping. At 0, you're overlapping. At -1, you're overlapping. At -2, you're overlapping. At -3, you're overlapping. Any of these numbers overlapping. Easy. Yeah. So it's kind of like if that distance is negative, you're overlapping, so you may as well just not even have another if statement. You just say, is it less than radius? So it's even easier. It's 2 lines of code, guys. All this nonsense that we've been doing here is just us trying to explain how you can easily solve this using math. If you understand the math, then you will see that you actually only need to add 2 lines of code to fix this. Literally 2 lines of code. If you want, you could do it in 1 line of code, but you should do it in you should split it into 2. Right? So, that's pretty neat. That is pretty neat. All of this I didn't actually need. I just did this for show. Okay? So, here's what we're going to do. Take the dot product of the get the displacement vector from I'm gonna specify it this way because I do want to think about it in this way, and you need to make sure you stay consistent with this. If you're not, you'll have to reverse all of your signs from the half space to the circle. You can do this the other way around if you get it from the circle to the half space, but then you need to remember this. Hang on, right? If you do from the circle to the half space, then everything will be reversed, and negative will mean that you are on this side, right? So it's gonna be slightly different, right? So um, if you do it the other way around, it'll still work, but you need to reverse a bunch of stuff. So if you did it this way, then if you end up subtracting the other way around, so from the circle to the half space, right, then you just need to realize that uh, in this case, negative dot product means you're on the outside of that surface, and positive dot product means you're on the inside of that surface. So it would be the other way around. But I think it's probably more intuitive to think of it this way, that negative means you're overlapping and positive means you're not overlapping. So I would like to do it this way. So last week I subtracted the other way around. I recommend you subtract this way around. Circle minus half space. Okay. Okay. So it's just going to be dot producted with, let's say, something like this. Dot product of that and normal. Then it's as simple as I'm just going to call this dot. Then it's as simple as if dot is less than radius, then overlapping. return true. Else, return false. Less than or less than equal to, it depends on if you want to consider if they're just barely touching, if you want to consider if that's an overlap or not. It's up to you. Same thing. It's going to be less than a pixel's difference. So, it depends on what you want to do. It depends on if you want to consider that touching or not. I don't know. It's up to you. You could say that's considered touching, or you could say it's not. I don't know. It doesn't really matter too much. Could you return dot less than radius? Absolutely. Right? Because it's if this is true, then return true. Otherwise, return false. So you can totally just return that. That's why I said you could do this in 2 lines of code. Because you could, I mean, you could do all of like this, and this can just be 1 line of code, and you just return that. So you could literally end up, you could write this, and then your second line could be return the dot product less than radius. That's it. That's your whole thing. That's the whole thing. Here's what I will do. Instead of doing this, what I will do right now is I will just show you what it would look like if I took the vector projection of this. I'm going to draw the vector projection. Hang on a sec. Let's do vector projection. So I've shown you the solution there. That is the solution. That's literally it. All right, sorry. This is literally it. That's it. Uh, but I also want to visualize something here. So vector 2, vector projection. Okay, it's going to be equal to the dot product, uh, vector 2 dot product. There we go. Of vector 1 onto vector 2. Okay, so that's going to be this one. Onto the half space has a normal. Okay. Oh, sorry. Float. Okay, and then the vector projection of this is going to be equal to the dot product times the normal vector. If this normal vector is normalized, I don't need to worry about this too much. Oh, there's one slight thing we have to worry about. There's no operand for float times vector, so you just have to do it the other way around. Because there is an operator for vector times float. That's it. That's like same stuff, same thing. Okay, that's just the little programming thing. That's one of the differences between the programming and the math. In math, the with the side that you put it on doesn't matter, but in programming, actually, it does matter the side that you put it on. So in math, there are some operators where the side you put it on does matter, though. Actually, it's just yeah, multiplication is symmetrical in math, kind of. It technically, if you expand out the math properly, uh, multiplication of vectors is not symmetrical in math. Um, if you're doing like matrix multiplication, right? If you're considering them as matrices. But yeah. Anyway, so here's our vector projection. Let's draw this. So we're gonna draw the okay from the circle's position. We're going to draw this vector projection. From the circle's position, we're going to draw this vector projection. We're going to need to make an adjustment to it, but I want you to see what it's going to do. Okay. Um, and we'll draw as well this midpoint. Sure, we'll draw some text here, but instead of drawing distance, we're going to draw the dot product. Okay, and this midpoint here is actually going to be instead, we're going to go from the circle, and we're actually going to subtract this vector projection. Hang on. And when we're drawing this line, we're going to draw circle to circle minus vector projection. There we go. So let's see what we get here. Oh, hang on. What I do? Oh, I forgot to return something. Here. Without showing you like 100% the solution, I'm showing you like 99.99% the solution without showing you the 100% the solution. Let's do this. All right, so check out the line we're drawing now. See that? And look, you can see it go negative as well. See how no matter what angle we have this set to, it's always perpendicular to the line? It's always perpendicular to our half space. And look, if I'm behind it, it's negative. In front of it, positive. So we always have that answer. So this little value here, the d that we have here, this is what we're going to use to determine if we should be turning it red or green. Right now I have it set to always turn everything red, but all you need to do is make it turn red or green based on the correct answer. So this, it should be green. This, it should be red. That's it. All right. So that's it for now. I will save my changes. Okay, I won't push it, but I will save it. And yeah, any other questions? Anything confusing to review? Anybody want to just talk?
I don't know what's gonna be on how to do assignment two though. What I'm gonna do assignment three, I'm gonna do it soon as I leave.
Okay, okay. So, all right. So what I'll do now is I'll stop the recording and everything like that, and then if you guys want to talk to me or talk to me about something you're working on, whatever, we could do that. All right. All right. Let's do it.